Welcome back. All right, we talked about the birth of the universe about 13.7 billion years ago. Now let's talk about the birth of the solar system. Now that has to deal with actually another theory, not necessarily the Big Bang theory, but something called the, wait for it, nebular theory. Okay? So the nebular theory states that the solar system coalesced out of a swirling cloud of interstellar dust and gas, which is called a nebula. Kind of a cloud of dust and gas out in space is called a nebula. And so this solar system began to coalesce from this cloud starting about 4.6 billion years ago. So from the birth of the universe, 13.7 billion years ago, it took over 9 billion years for the solar system to start about 4.6 billion years ago. So all of this dust was kind of swirling around. Every piece of matter, no matter if it's a large planet, if it's a car, or if it's a single molecule or an atom, anything that has matter, mass, that exists, exerts an attractive force of gravity. So even these little particles of dust and gas began to swirl and come together under the force of gravity. As that occurred, the sun was born from a nuclear reaction called fusion as things became closer and closer together. And it's also, more on this here in a minute, but it's also the explanation for why the inner planets of our solar system, the nebular theory that is, it explains why the inner planets of our solar system are all rocky planets, and while the outer planets of our solar system are more ice and gases. So here's a little visual on the nebular theory. So again, we have this nebula, this random collection of dust and gas out in space. And due to gravity, these pieces of dust and molecules of gas began to kind of attract to themselves and come together and compact and began to spin. Now, as that happened, the material began to kind of come together and more under the force of gravity and spin and flatten out. So when that happened, as the molecules become more compact and more compact due to gravity, then more material gets more compact and compact due to gravity, so it becomes a bigger force. And at some point, those molecules and atoms were fused together. And that was the birth of the sun. That's what kind of turned on the sun. And that's what that central bulge is becoming, is the sun kind of beginnings there. But the gas itself, instead of a big cloud, kind of turned into this disk. As things kind of spin, there's a little physics involved there, but it kind of flattened out into this disk. You get this big bulge in the center that would eventually become the sun, and then you get this disk. So the contraction of gravity kind of in the center raises the temperature, again begins the process of nuclear fusion in that central bulge, and that's when the sun turns on. The outer disk then begins to cool. Now it contains kind of more rocky material, heavier material, and the material begins to kind of separate out into disks. The larger chunks kind of attract to one another, and eventually these disks, all the material that are in all these disks, coalesce together to eventually form the planets. Now, that takes millions of years to occur, but that is the process of how our solar system went from this cloud of dust and gas to what we see today, our star, the sun, and planets and everything else that exists in our solar system. So, great question. Well, what's the evidence? How do we know? We see it. We have pictures of this happening elsewhere in the galaxy. So we can see other solar systems beginning to form, from nebulas to things starting to spin around, to forming the disks, to these separated rings that eventually form planets. The compression and when the kind of star kind of turns on. We have pictures. Right? We see it. We see it happening. Oh, that's how it happened? Got it. Visual evidence. There you go. So the way all of this stuff formed is through the planets formed, specifically Earth, and all of them, is called planetary accretion, accumulation. Stuff accumulated to form this stuff. Stuff accumulated to form the sun. The gas and dust eventually accumulated to form Earth and Mars and Jupiter, etc. So, the sun is in our solar system. The sun is just a little bit older than the planets. The sun, again, about 4.6 billion years old. The Earth around 4.54 billion years old. So, a little, what's that, about 60 million years. The sun is about 60 million years older than the Earth. That kind of formed first, and that disk kind of took some time, millions of years, to eventually form the planet. So the sun's just a little bit older. The outer portions of that nebula, again, cooled into the disks of debris, and the random collisions of that material out there begin to build up bigger stuff and bigger stuff and bigger stuff. This resulted in planets that were eventually spherical, not flat. The Earth is not flat, spherical. That's how gravity works. It works in 3 dimensions, not a flat plane. And then also the planets being isolated, that's due to those disks separating out and all the material kind of clumping together. Yep, that's what I said. Now, there is some stray material in our solar system that never really clumped together. We have asteroid belt between Mars and Jupiter, and we also have some material on the outer edges of the solar system that never really clumped together. So we got a lot of different stuff in our solar system. So we are part of the Milky Way galaxy. So again, the universe is about 13.7 billion years old. The Milky Way galaxy, about 13.6 billion years old. It formed about 100 million years after the universe formed. The sun, again, about 4.6 billion years old. We have 8 planets. They kind of all formed around the same time, 4.54 billion years old. Sorry, Pluto is not what you would call technically a mainline planet. It is a dwarf planet. So sorry. Does anybody know Pluto's connection to Arizona? If you do, send me an email. I might give you extra credit. How about that? There's also 290 natural satellites. That's the technical name for them. Commonly, they're referred to as moons, but that's actually technically incorrect. There's only one moon in the whole universe, and that's our natural satellite because that's its name. Just like there's only one Earth in the whole universe because that's the name of our planet. There's only one sun in the whole universe because that's the name of our star. So sometimes people use the word moons to say all natural satellites. Just like an artificial satellite goes around the Earth, a cell phone satellite or whatever, natural satellites naturally go around a planet. In this case, our natural satellite is named the moon. But Mars has 2 natural satellites, Jupiter 95, Saturn 146, Uranus 27, Neptune 14. Pluto, even though it's not a mainline planet, does have kind of 5 little natural satellites. There's also a tremendous number of asteroids. Asteroid is defined as kind of a wandering rocky body of space material that's 10 meters in diameter or bigger. Most asteroids orbit the sun somewhere between Mars and Jupiter. There's also millions of comets, which is just ice-covered asteroids, as well as meteoroids. Meteoroids and asteroids are kind of the same thing. Asteroids are 10 meters in diameter or bigger. Meteoroids are less than 10 meters. It's a little bit smaller. There's a bunch of dust and gas out there as well. This is the configuration of the solar system. Be careful here. This is misleading because this is not size-wise correct, but it just gives you, and definitely not distance-wise, it just gives you an idea of where these planets are. Mercury, Venus, Earth, and Mars, all being kind of the inner rocky terrestrial planets. And we have that asteroid belt, and we have Jupiter, Saturn, Uranus, and Neptune. Gaseous planets known as the Jovian planets. And then here's Pluto. Real quick, one reason Pluto isn't a mainline planet. All the other planets kind of orbit in this particular plane, and you see Pluto's orbit is just kind of this weird random up and down and over and under type thing. That's just one of the reasons Pluto is not a mainline planet, and it's been relegated to a dwarf planet. As far as size is concerned, not distance-wise, but size of the planets compared to the sun. The sun's big. It's really big. So compared to the sun, this is the size of the different planets. You can see Earth relatively how small it is compared to the sun. Here's another view of that. Now, again, distance-wise, this is not correct. This just shows size-wise where these things are at. Distance-wise, it's pretty hard to imagine how far away these things are from the sun. Look it up, look at videos. It's kind of mind-boggling, but this is just size-wise. But again, we have the inner terrestrial planets. These are rocky. These are all solid surface. They're small but relatively high density, solid rocky stuff. And then we have these Jovian planets. They're much larger but relatively low density. They're more gaseous, maybe with cores of liquid or ice, but they're mostly made out of gases. So why the hell is that? Well, all attributed back to the nebular theory. Again, we have the rocky terrestrial planets, and we have the larger gaseous Jovian planets. So again, what the hell? What's going on here? Why are the inner planets rocky and those outer planets not? Well, the inner part of the solar system, as it was forming, as the sun kind of turned on, very hot, a lot of heat, 3,000 degrees Fahrenheit. That's enough heat to really evaporate off and move away any lighter gaseous elements like hydrogen and helium. So those gaseous things were kind of burnt off. They kind of escaped. It was like, oh, this is too hot. And so they kind of escaped out to the outer reaches of the solar system. And what was left behind was those heavier elements and compounds that would eventually make rocky material. So that's one reason. The heat kind of drove off a lot of the gas. We still have some hydrogen and helium in the inner part of the solar system. I mean, there's hydrogen, H2O. There's two hydrogens in water, which is on Earth. We mine out helium for helium balloons. So these gases still exist on Earth. It's just the vast majority of those got cooked off in the early beginnings of the solar system. Also, when the sun turned on, there was kind of a seismic explosion, a massive concussive wave. Once that sun turned on, nuclear fusion is essentially an explosion. It's billions of nuclear bombs all going off at once every second. And so when that sun turned on, that really kind of pushed off that material kind of further out, again, leaving behind some of the heavier rocky material. And the third reason is gravity. Gravity wants to hold on to heavier stuff, and as this nebula was spinning around and this disk formed, that lighter stuff kind of got flung off. The gravity of the sun wanted to hold on to the heavier stuff, and the lighter stuff, like gases, like hydrogen and helium, were able to kind of make their way out a little bit further. Okay? So we talked about the beginning of the universe and the evidence. We talked about the beginning of the solar system and the evidence. So the Big Bang Theory, the nebular theory. Now we're going to focus on Earth. All right? But that will be in the next section, next video. I'll see you next time.